So now let's go about finding an exact solution to this system using a new method called the substitution method. So the first thing that we want to do is we want to be able to solve one of the equations for one of its variables. And if we look at each of these, our first equation, the x has a coefficient of 2, the y has a coefficient of 1. So this variable would be rather easy to solve for. Here in our second equation, the coefficient on x is -3, coefficient on y is a +2. Okay, so if we're looking at this first equation, if I want to get y over here all by itself, I would just need to subtract 2x from both sides. So if I take 2x plus y equals 12, if I start with the first equation, and I'm not starting with the first equation because it's the first equation, but because it has a term in it that has a coefficient of 1 on its variable. So if we subtract 2x from both sides, we'll get y equals 12 minus 2x. So the first thing says to pick one of the equations that looks easiest to solve for one of its variables. So we took the first equation and we solved for y. Now it says to substitute the expression from the first step into the other equation. So if we think back to the graphs, where those graphs, if they cross, they have to share a common x and a common y value at that intersection point. So we're going to take, if y is equal to 12 minus 2x, we're going to substitute that in the other equation for y. So in place of y, here we're going to put in 12 minus 2x. So now we have one equation with only one variable in it. So we're going to solve for that variable. In this case, we're going to solve for x. Okay, so if we box off our terms, so every time we end up by a plus or a minus sign that's not in grouping symbols, it's the start of a new term. Oops. Let's get that back on here. I accidentally erased what I had there. So here we have a term, and here we have a term, and here we have a term. Okay, so in the second box here, we've got some parentheses to remove by distributing. So we're going to get -3x. And then the second term, once we distribute the +2, we're going to get plus 24. A positive times a negative is going to give us a -4x equals 6. Now, here's a term, here's a term, here's a term. So on the side we have a couple like terms. We've got -3x, and we're going to take away 4x. So we've got -7x plus 24 equals 6. So now there's no more like terms on this side to combine. There's no more like terms on the other side to combine. Okay, so now we're going to try to get x over here by himself. So first we're going to subtract 24 from both sides. And we'll get -7 times x equals -18. And then we're going to divide both sides by -7. And we'll get x equals 18/7. So now, when we're solving the system, we're after an ordered pair x comma y. So we're not quite done. We only have the x coordinate of that intersection point. We also need the y coordinate. Okay, so we're going to go back up to step 1, and we had y equals 12 minus 2x. In the first step, we solve for the other variable. So we already have a nice equation that's already been solved for y. Okay, so we're going to take y equals 12 minus 2 times 18/7. Okay, so on your calculator you can hit 12, subtract 2, parentheses, 18 divided by 7 parentheses, and math enter enter will try to convert that to a reduced fraction if it can. And in this case it can, and so it gives us an answer of 48/7. So our solution to this system is 18/7 comma 48/7, so at this ordered pair. So looking at your graph on the previous page, does this answer seem reasonable? And explain. Well, if we take 18/7 on the calculator, this is approximately 2.57. And if we take 48 and divide by 7, we get approximately 6.86. Okay. So we had said on the previous page that x should be between 2 and 3, and it is. And we had said that y would come out between 6 and 7, and on our graph it looked really closer to 7 than 6, so it makes sense that we got something like 6.87. Okay, so our graph kind of helped us, we knew we could kind of narrow it down to between which integer values that it came out to be. But again, the substitution method gave us that exact point where the graphs intersect. So again, if we went back to the graph, this would be the point of intersection. Okay. So again, this is our point. It satisfies the first equation and the second equation. Okay, therefore, it is a solution to our system. It's now an example 2. In the last section, we used linear regression to find a linear model that relates number of years since 1980, which we called T, and life expectancy for 2 different subgroups, one for women and a different model for men. Okay, so we had put this into L1, and this was in L2, and this was in L3. And so when we did the linear model, so we did that lin-reg, and on this one we used L1 and L2. And this is what our calculator gave us for that model. And then for the men, the input was still years, L1, but then the output was in L3. And we got this model for the male data. So the first part asks us how we can tell from the equations that these lines must intersect. Okay, so in here, if we're looking at, I'm just going to look at the first few decimal places on the slope, so this coefficient on x. So these 2 lines have different slopes, and if lines have different slopes, they must eventually intersect somewhere. Okay, so slopes are different, okay, so lines must intersect. So now it says to find an approximate solution to the system using the substitution method. Okay, so we have both of our equations already solved for y. So in this case, we're just going to take 0.117142857x plus 77.45238095. So this whole expression, and substitute it in for y hat in our other expression. So equals 0.2097142857x plus 69.86190476. Trying to scrunch that in there. Okay. So on each side of the equation we have an x term and a constant term. So there are no like terms to combine on either side. So we're just going to start moving terms. Okay, so in this case, we can, let's see, if we subtract our x from both sides, because that real world data never has very nice numbers within it. Let's see, 42857, actually we forgot the 1 in there. 1x. Okay, so if we subtract that from both sides, we're going to get 0.0925714.286x. And at the same time here, if we bring over our constant term, so subtract 69.86190476. That gives us 7.59077619. Okay. So now, keeping in mind we're trying to get x over here by itself. To solve for x, our last step is to divide both sides by this 0.09 number. So if we take 7.59077619 and divide by 0.0925714.286, we get approximately 81.999, or roughly about 82. Okay, so if we go back to the context, T was years since 1980, so we could say 82 years from 1980, we predict, okay, and the output here was the life expectancy, so we predict life expectancy for men and women to both be, and if we plug in that value of x to either equation, let's see, this gave us our x value, and if we plug that in, we got a y hat value of approximately 87.1 if we round off. So again, we can take this 81.999 and plug it into either equation. Since it's the intersection point, y hat will come out the same. So in 82 years from 1980, we predict life expectancy for men and women to both be about 87.1 years.